Hello, nice to meet you. I'm Tuomas. My part of the discussion is nice and easy, just some general stuff about AI and some funny tips that I have found during my years in Teamit and other stuff I've been doing. First we're going to talk about a bit about the different areas, simple stuff for the different types of things we can do and different types of things we want to do. Then we're going to talk a little bit about strategy and expertise, what's involved in these projects. And then the funniest part, I think, is the practical stuff about some tips and tricks I've found. First, the topic is AI and data science, but what is AI and data science? Well, AI is quite loosely defined, but we have now a strict definition that a machine carries out tasks that require some inference, some sort of programming involved, algorithms, and then we have data science. What is data science? Well, data science is more about statistics and mathematics and about the practice of carrying out this AI stuff. AI is whatever hasn't been done before, is a quote that is quite funny in my mind. Then if we compare these foundations of these topics, then I don't see if there is like a strict definition between these, because the AI is more about the solution and the data science is more about the practice of carrying this out. So this is kind of like doing the same thing, but looking at a different perspective. If one would like to find out different kind of examples for these, AI could be like a classification of a product into faulty or okay. Then for data science, this example could be if we would analyze some statistics of this production line for these products, for example. Then there is this hot topic of machine learning. And this machine learning is like in many ways the core of the current state of these hype solutions that have been carried out. It's the way of doing solutions by learning what to do using the machine itself. We don't need to manually program it to let it do what we want to do. This is not anything new. It's quite old field of science, but it has become popular in recent years, and mainly because there has been more computational power and lots of data nowadays available, and this has become then like a good place for good results to come out. And then because there's good results, then this incites people to do more algorithm development, and then this will go on and we will get nice results. There are lots of different types of other fields of AI and data science that are very closely related or are more deeply in focusing in different types of tasks. For example, there's data mining, simulation and statistical stuff, but those all are kind of like the tools that can be used in carrying out different kind of solutions, whether it would be like this AI type of solution or then a more analytic solution, for example, in the data science domain. Then some of those things that we want to do with these tools gives us different paradigms that we can then classify these solutions into. For example, we have this problem that we want to understand and explain existing data we have. This could be then called a descriptive domain. And if we think about these kind of problems, for example, if we would have, for example, a project, and we would then apply these kind of paradigms with this project type of solutions, we could then in the descriptive domain, we could analyze the project. We could, for example, look at the KPIs of the project and see what kind of value we have with this project. And then we have the predictive domain, which is about looking into the future or maybe trying to infer something that we haven't seen before. We want to, for example, predict the performance of this project in the future, or we could predict if this project will fail or not. Then we have something that is closely related to this predictive domain, which is a prescriptive domain. And in this sense, we want to use those information into deriving some sort of recommendations. For example, that please do this. This will give you better yield, for example. And then, lastly but not least, we have the generative domain in which we want to generate new data. We want to, for example, we have specifications for a new project we want to carry out. And then we could, for example, use this AI tool to generate templates for a new project. Of course, these different kind of problems are often very closely connected in real life, so we might have need for all of these in the same problem setting, but these are like the foundations of building up these solutions. Then we're gonna talk a little bit about the strategy of managing and carrying out this type of development in an organization. In this type of projects and organization level expertise contain lots of different people and lots of different types of expertise are needed in those. Some of those core expertise areas could be divided into three categories that are more to do with the data science and the AI itself. Here we have the data scientist. I'm a data scientist. And then we have data engineer, and then we have a domain expert. These roles are not strict. They can be very interleaved, or one role can be combined into multiple tasks. But the tasks that are focused on different types of roles are so that, for example, the data scientist is more focused on the methods, and the data engineer is more focused on coding and implementing the solution. And then we have the domain expert, which then carries out the information about the environment and about the problem, about the goals into the team itself. Because we often have this kind of gap between those knowledges. We have the knowledge about the methods and the ways of carrying out different kind of solutions. And then we have the knowledge about what we want to do and what kind of environment we have. We are in a setting in which the cooperation between these roles are emphasized. This kind of cooperation between roles is also important, of course, in different kind of settings also, not just in data science and AI. But for this AI setting, the knowledge about the system is more focused, because this knowledge very much gives us better results if we can carry that out in our solution. We can use this information to get better results. If there is small detail that the domain expert knows, and this can be used in the model, then we might have like a solution that works. But without this information, it can be a situation in which the solution just doesn't work. Small things can pay great details in these kind of solutions. Then, if we would have like a setting in which we have an organization level decision about managing these type of concepts in our organization. For example, we might have policies about doing different stuff with AI, or we might have policies about we want to carry out this type of projects, and there is this data governance type of thing going on in the organization. And then we're gonna deal with these types of aspects that are very high-level strategic components that are often dealt with. These are the three of those that I have found that are very in the core of carrying out the governance of the AI stuff. And first of those is like the trade-off between, do we have the data first or do we have the use case first? We might have this policy that we just gather lots of data and then we find out what we can do with that. But then again, we can have this situation in which we first very carefully check out what kind of problems we have, and then we have this future plan that, oh, we might have a solution for this, but wait, we don't have any data for that. So we are always doing a trade-off between these two types of domains in this policy. Of course, there is not like a single answer which is the best way to do. We need to do it as every time we need to check out what is the best situation. Then we have the trade-off between doing experimental stuff and then doing the simple stuff. That's easy. We can optimize the whole processing at the same time, or then we can choose some component of the process and optimize that first. Then we have this solution that could be like a black box that takes all the data in and gives us all the answers in the same go. But then we want to maybe be more careful and do this knowledge first approach, in which we carefully have all the data and then we have all the knowledge and then we manually insert all the knowledge we have into the model. It's not evident which is the best way in every case. We need to always pay great attention before we set up different kind of policies regarding these. And then, well, maybe the trivial aspect, but of course, the low-hanging fruit is always very nice. If we have something simple and that is very efficient, that's nice to do. Maybe a good analogy would be the Occam's razor. Often the simplest solution is the best one or the correct one. Although if we would use that as a strict rule, then we would be in trouble, because there's criticism between do we want to be more complex or do we want to do the simple. Then if we would have like a complete setting of a different organizational stuff ready, and we have policies and all together, then we start carrying out these projects. And with these projects, we often have different situations and problems that arise. And these are something that would be nice to know in advance before we run into those. Only by acknowledging them, we can save a lot of time and effort in many different areas. The first, the high-level aspect of doing this kind of project is the foundation of these solutions we have. We have some kind of solution and it involves data and model. That is all we have for the solution. And when we consider these, it's important to think about the data and the model as separate things. If we have data, does the data relate to the question we want to have answers for? And then if we add a model, does the problem and the assumptions that we make align with the goal that we are trying to make? These are very simplistic ideas, but if we think about them in advance, we can maybe focus on the right parts of the project. Uncertainty is always involved in these solutions, and often when we start off with a project, we want to have the perfect solution and the perfect prediction for some type of task. But often we kind of like forget that we have uncertainty with all those solutions. Nothing is certain in those solutions. We need to acknowledge that. And if we think about the goal, instead of trying to get the perfect estimation, we could think the goal is to have just as small uncertainty as possible. Then we can maybe set the goals better and understand the situation better. And this is now closely related to how we define the problem in the first place. Often we have an idea. For example, in this case, we have an idea. We want to have a system that detects different kind of anomalies in our some signal that we have in our system. But we don't have the idea about that in more detail. We just want to do the solution, and we put this stuff into our black box model, and then we get some kind of solution. And then we get the solution, and we are very happy, and we apply that. But in what part we forgot to define what kind of anomalies we want to search for. Often there are lots of different details about these models and these problems that are very open in the first place, and then these problems carry on, and then when we continue doing the project, we forgot to frame these open questions, and we just push on and get the solution. It's important to think that we need to clearly focus on this definition of the problem in the early stage already, so we don't forget those. And then we have the solution, and we got the results, and then we are very happy, and we are eager in using these solutions in our favor. And we often look at them in certain perspective, and we do errors. We use different fallacies and misinterpret these. For example, we have a solution that is 98% accurate. Well, without more information, this doesn't tell us much. Because there is this fallacy that actually the solution is in such a rare case in the first place that the usage of this solution doesn't really make any sense anyhow. This type of example is very not like a typical example of those misinterpretations, but it's important to acknowledge that these kind of solutions need to be inspected carefully, and it requires some type of statistical and domain expertise that can be applied to the solution and to the resolutions, and then we can check out and analyze carefully if this is valid or not. And then we're going to shoot about these nice problems that we have. So when we start the project, we have often unrealistic expectations, and we want to do too much too quickly. We forgot to frame the problem, and we forgot to do the planning carefully, and we maybe underestimate the resources that we need. But this is kind of like an easy problem, because we can address these problems just by paying more attention to them. Then we have different kind of problems that are more harder to solve, maybe technical problems. Some systems maybe doesn't interact well. It might be a blocker for the project. And then there is moral or ethical or legal barriers. For example, there could be a system in which customer has a right to receive like an explanation for the decision. And if we have these kind of very popular neural network solutions, there is just no possible way of explaining why some decision was made. And a bit related to that, if there is a situation in which it is absolutely not accepted to have an error, if we have a machine doing those type of solutions that then results into an error, that can be a blocker for some projects. If it's for example a human making the error, then we can maybe just accept it. But if it's like made by a machine, then it cannot be accepted. And then some more problems. Often we start off with a test solution, and we have like a working solution that is nice and all, and we have the test data we have used for developing this solution, and it seems nice, and we start building up like production-ready solution for that. But then we notice that this doesn't run anymore in this more numerous situation, and then it can be a situation in which it runs, but it just doesn't work anymore. This kind of scalability is something that needs to be considered also in the early stages, before we do the heavy effort of doing the product-ready version of the solution. And then there is a problem in which the solution that we have carried out, for example, the proof of concept solution, works nice, but then when we are ready to making that into a production, we see that, oh no, our system and our problem changed. We need to start over. Maybe the environment is changing so rapidly that we just don't have time to develop the solution. And maybe the system is developing all the time, and the solution would be something that takes this into an account. Then there is this very nasty problem of limitations in the data. We might have the situation that the data is not enough connected with the problem that we want to solve. That is something that we often overlook this by just thinking that, oh, but this comes from the same system, but maybe there is something more into the outcome that we don't see from the same data. Also, the data can be very unstructured, or it's hard to access, or there is just noise in the data. These kind of problems are not maybe blockers, but it depends a lot on the task and on the level of noise, for example. Then maybe the most important thing that when building up these kind of solutions, we often overlook what we are dealing with. And there is this nice analogy that relates to this horse that was, it was believed that this horse was very clever and intelligent, and that this horse could calculate. And it was made so that somebody asked a question from the horse, and the horse used the foot to tap the answer. And everybody was amazed, and everybody really believed that this horse is actually intelligent, and nobody suspected anything. And then years passed, and then there was this scientific study about that, and scientific study didn't see any problems with this. They concluded that the horse is intelligent. The horse knows how to calculate. Then more years passed, and then they realized that, oh no, it was just that the horse was very clever in looking at the questioners, like behaving, and then he used that as a way to answer the questions. The horse didn't really count by himself. It was just a different kind of intelligent. It was more socially intelligent that the horse used. And how this connects to the AI and this topic of today? Well, often we have these kind of solutions that we just don't realize what they are doing, or what is the core of those solutions. And this all comes down to the question that, oh, we have this AI, is it really intelligent? And oh, we have this machine learning, it's learning, it's nice and all. But we need to remember that it's not the same kind of intelligence and learning that we think as a humans. It's very clever nevertheless, but it's just different. And this also connects to maybe in the same way that we think that we are trying to somehow relate these solutions into human behavior. And we want to, for example, look at those superhuman aspects of them. But then if we take an analogy, for example, out of a submarine, a submarine can dive better than a human. Yeah, of course it can. It's not interesting that it is superhuman in diving, but then what is more interesting is what we can do with the submarine. We don't just go on and, somebody invented submarine, I want to have a submarine too. We need submarines, you need to have a submarine too. No, we need to find those use cases, and we need to find those interesting application areas that we can apply that submarine into. And if we remember that, we can then maybe utilize those tools more efficiently. And if you don't remember anything else, I like that this is the most important stuff about my speech. Thank you, and if you have more questions, I will answer those.